All right. Hello, everyone. My name is Shardul. I'm Platform Power Design Lead at AMD Data Center GPU.
And my name is Thurein Paing. I'm also on the same team.
So today we're going to talk about power delivery challenges for the AI accelerator cards, advancements we've been driving, and development of the ecosystem for higher density power modules. So with the demand for AI applications being skyrocketing, the compute density requirements at rack level has been increasing exponentially, and that drives the power density requirements on the AI platforms. So for example, just for a comparison, AMD Mi250X to AMD Mi300X, there is about 33% gen-over-gen power density increase. And with the recently announced Mi325X last week, we are delivering about 1 kilowatt of total board power with the same form factor as Mi300X platform. So that's about even delivering 30% more power with the same platform size as that of Mi300X. So I hope everyone can appreciate the power density challenges that we are facing. At AMD, we typically implement a two-stage power delivery architecture. First stage being the 4-to-1 intermediate bus converter, unregulated. Second stage being the two-phase high-density power modules. More on these two modules in the later slides. So on Mi250, we used a 10 by 10 two-phase power module. And to meet the Mi300X power density requirements, we use even higher power density 9 by 10 two-phase power modules. So that's about 60% increase in the current density just from Mi250 to 300X. And to make the PDN challenges more pronounced, I would say, to support the increased compute needs, the GPU packet sizes are increasing. With that, the GPU keep-out zones, just from the package, the mechanical keep-out zones, the mounting hole keep-out zones, areas that we have to avoid to get away from any of the SI concerns. The power component placement and PDN design challenges are getting even more difficult with the next generation AI platforms. Chiplet architecture, as most of you know or are familiar with, it provides great performance, flexibility, and compute efficiencies. But for platform designers, it just poses another challenge of supporting multiple domains on the platform, multiple power domains on the platform. So that typically involves having multiple controllers, and that comes with multiple IOs, PWMs, current sense, voltage sense, T-sense, all the sideband signals that you have to route. That makes the power delivery design even more challenging. Having said that, for the next generation, the upcoming AMD AI platforms and the next generation of AI platforms, even these 9 by 10 two-phase power modules cannot meet the current density requirements. Now talking about two-phase power modules, most of the power semiconductor suppliers know about what these modules are. They are manufacturing it, working with us closely. But these power modules are nothing but DRMOS, basically FETs drivers, integrated with inductors and capacitors to make this compact, high-density two-phase power modules. So AMD has been a key driver to drive the power, this high-density power module ecosystem. And if you compare back in 2022, we just had one qualified solution for these two-phase power modules, basically mass production qualified by AMD, and we were working with 3 other vendors in parallel to work with them, qualify them, and be MP ready. Fast forward now, we have 3 solid two-phase high-density power module solutions qualified by AMD, and they are mass production ready. And we are working with another 6 different solutions to make them qualified as well for mass production and then contribute and drive and continue driving this ecosystem. Having said that, for next generation AMD AI platforms, these modules still shy from meeting the current density requirements. And the upcoming AI platforms from AMD, the PDN noise tolerance requirements for the GPU rails, and of course the HBMs are getting tighter with even higher load steps and even higher DIDTs. So existing two-phase power modules which exist in the industry today, all of them are common footprint, which are implemented using the discrete inductors. What we really need is common footprint definition with the TLVR or coupled magnetics in order to improve the transients. That's what AMD been working with our industry partners and vendors closely. Now, although these high-density power solutions provide higher densities and meet the current density requirements, these are basically the ecosystem is still evolving, is not really mature compared to SPS and discrete inductor-based solutions, which exist in the server domain from a decade or so. Although we are pushing the power density and the technology in these power modules, there exists a greater risk of quality and reliability. And that's why we see a lot of people, they don't want to use modules much. But AMD has been early adopter of these modules and go into the mass production on the AI accelerators. So we really worked hard with our customers, partners, and module vendors to define reliability test plans, burn-in qualification plans, in order to improve the module-level reliability, board-level reliability, and overall system-level reliability of these AI systems. Now going to the IBCs, these are, as most of you might know, is intermediate bus converters. These typically come with regulated and non-regulated. On the AI card, so far AMD has been using 4:1 common footprint, fixed ratio intermediate bus modules. Now with the typical data center thermal boundary conditions that we have, basically PCB temperature and topside heatsink or cold plate temperatures, these modules do not really meet the power density requirements. For example, vendors would say, oh yes, it's 1 kilowatt rated IBC. But really, if you consider the V in corners and thermal boundary conditions that typically exist in today's data centers, those modules may be at 750 or 850 watt at max. So what we really need to do is to improve the densities of these modules to really enable higher than 1 kilowatt accelerator platforms, come up with the better thermals. Definitely innovation is required on the thermal aspects of these intermediate modules. It's not really, I mean, of course, the electrical challenges are daunting, but it's mostly how you manage the losses, and thermal management is I think, utmost important. And lastly, with this AI, ever evolving AI workloads, these IBCs need to support peak power excursions, which are higher than 2 times TDPs. Now there are multiple drivers in the industry, just like us, who are driving different fixed ratios, 8:1, 10:1, 12:1, and so on. But what we really need is a common footprint definition of these IBCs, which can absorb different ratios of these IBC, 8:1, 10:1, 12:1, etc. Because we believe every platform is different. Just even within AMD, every platform is different. So we need, as a platform power designers, we appreciate the ability to optimize our platforms and designs to meet end-to-end efficiency targets and by meeting the power density requirements. So that's where this common footprint definition, which can incorporate 8:1, 10:1, 12:1, and even more higher fixed ratios would really help. And with the IBCs, as these are basically the power modules with multiple PCBs sandwiched, multiple components such as FETs, gate drivers, DRMOS, magnetics, transformers, capacitors, controllers, everything integrated into these packages. So the package reliability, the module package reliability, solder joint integrity, board level reliability are even at greater risk with these IBCs than the two-phase power modules. So all the challenges that I highlighted before about stricter burn-in requirements, stricter production test coverages are even more critical for the IBCs. So having said that, I'll pass the mic to Thurein.
Great, thanks, Shardul. All right, so to summarize what Shardul has covered and also our call to action, right? So, we're seeing an increase in power levels, generation over generation. It's not just us. There are presentations about 400 volt racks and things like that at this conference, right? So what we see a need for is greater than 2 amp per millimeter squared power modules at the final conversion stage, right? And to support these high current densities, we'll need optimized intermediate bus converters, conversion ratios, optimized efficiency, as well as thermal performance, right? And along with those two modules together, the hope is that we'll develop an ecosystem with reliable, high-quality modules that can be used across the community, right? And so, the timeline for AMD's contribution to this ecosystem. We are already working with some of our power component vendors on some of these definitions, and we'll be releasing in Q1 of next year a new power module definition to achieve these high current densities, right? And along with this definition, standard of reliability and quality standards and test procedures to ensure these complex power modules are reliable and mass production deployable, okay? And so to get involved, please, contact any of the authors on this paper. And yeah, we look forward to working together with you guys. All right, thanks.
Questions?
Is this an OCP work stream, or this is just an AMD initiative?
This is so far an AMD initiative to improve the quality reliability of these high-density power modules. As yeah.
I see. So just contact you individually as opposed. Okay.
Yeah.
Got it.
Can you mention who the vendors are? Is that open source or not?
Not yet. Thank you.
Hi, I'm Rob Chiacchia with Ridge Tech. Do you see room or a need for modules, these two-phase modules with TLVR and non-TLVR magnetics?
Yeah, so I think especially as you have heard, maybe challenges with the HBM3, HBM3E, and HBM4, the PDN noise tolerance are getting even more tighter. And also on the next generation AI compute platforms, we do really see a need to basically ability to meet even tighter transients, right? So it would be, we foresee it would be a combination always on the platforms where when you have I/O or some rails which are not really tight to meet the PDN. So for those, we'll use the proven non-TLVR, the discrete inductor-based power modules. And wherever we feel a need for the rails I mentioned, mostly the core and the HBM, I think those are the perfect candidates to try to use the modules with improved magnetics, whether coupled inductors, TLVRs, and maybe high capacitance integration as well into the modules.
And one more question, mounting, would these be top side and bottom side mounted on the board?
So we are exploring all the options. So yes.
Right, thank you.
Hi, I was wondering, with the higher efficiency of SiC and GaN devices, but where you can't actually put a lot of control in, can you see moving the control for those kind of devices into your compute chips? And doing a sort of co-design between your compute chips and the high power side?
I think there exists some work already by some of the silicon providers on that, but at AMD we are, at this point, not really actively pursuing that for now. Yeah. Any more questions?
Just pick up on the previous question. So what is like industry direction? Is that what is prevent to define the common footprint as an industry effort to make it open, everyone can design or contribute to the same module?
Yeah, I think that's why we've been taking this initiative, because there are like multiple definitions that exist for the power modules. We want to make I mean, we are talking with mostly the the power semiconductor companies, but I think we wanted to drive this to the bigger stage and make sure, there exists a common standard for the power blocks. And I think that's what this presentation is mostly geared towards, because these modules are complex and really needs a lot of work done on the reliability, quality, and the testing of these modules. Electrically, of course, is a challenge, but I think as we highlighted, right, thermals and quality reliability is utmost challenge. So we want to make sure we are, combining all the lessons learned through our experience from 2022, starting from Mi250, 300X, 325, and so on, and then contribute to the industry through this to, develop this ecosystem even further and keep driving towards better, more reliable power modules.
Yeah, I totally understand the complexity. I saw you mentioned several times about the common footprint. I think
Yes.
that seems like a relatively easy step to
Yeah.
standardize.
Yes.
And reliability or efficiency or Z height, all this can be like optimized later.
Yeah.
Just feel like that could be like an easy step.
Yeah,
Thank you.
definitely. Thanks.
All right. Thank you, Shardul. Thank you, Thurein.
Thank you.